Universidad Autónoma del Estado de México.
We are going to talk about transport phenomena and heat transfer.
And we are Dani, Pepe, Ceci, and Peter.
And we hope that you enjoy our video. Phenomena is important for chemical engineering because they are at all stages of an industrial process. Transport phenomena is important because they will allow us to identify the fundamental laws of the transport process of mass, momentum, and energy. Provide us with the power to develop theoretical able to be used in quantifying the approximate real systems, determine its validity and scope.
The subject of transport phenomena describes the transport of momentum, energy, and mass in the form of mathematical relations. Descriptions is found in the laws for conservation of momentum, energy, and mass in combination with the constitutive relations that describe the fluxes of the conserved quantities. The most accurate way to express these conservation laws and constitutive relations in continuum mechanics is to use differential equations. Solving the equations that describe transport phenomena and interpreting the results is an efficient way to understand the systems being studied. This methodology is successfully used for studying fluid flow, heat transfer, and chemical species transport in many fields, including engineering sciences, biology, chemistry, environmental sciences, geology, material science, medicine, meteorology, and physics, and so on. Any chemical process can be macroscopic level, microscopic level, and molecular level. At the macroscopic level, we write macroscopic balance equations which describe how mass, momentum, and energy change in a system. It gives insights into the global assessment of the problem, and for many of the industrial engineering cases, this should suffice.
At the microscopic level, we study that it is happening to the fluid mixture in a small region of space. Mass, momentum, energy balances are this small region of space rather than the whole entity. This gives us valuable information of the temperature, velocity, and concentration profiles.
At the molecular level, we try to study T-strip transport by means of molecular structures and intermolecular force. Intermolecular forces are also responsible for the transport phenomena. The basic equation for momentum, heat, and mass can be derived directly from the Boltzmann equation of statistical mechanics.
Mass transfer is often coupled to additional transport processes, for instance in industrial cooling towers. These towers couple heat transfer to mass transfer by allowing hot water to flow in contact with hotter air and evaporate as it absorbs heat from the air. Mass transfer is used by different scientific disciplines for different processes and mechanisms. The phrase is commonly used in engineering for physical processes that involve diffusive and convective transport of chemical species within physical systems. Some common examples of mass transfer processes are the evaporation of water from a pond to the atmosphere, the purification of blood in the kidneys and liver, and the distillation of alcohol. In industrial processes, mass transfer operations include separation of chemical components in distillation columns, absorbers such as scrubbers, adsorbers such as activated carbon bits, and liquid extraction.
Energy can be transported in three modes: molecular energy transfer, conductive heat transfer, convective energy transfer, and radiation. The mechanism of transport thermal energy is done in two steps. In the first step, molecules migrate by random motion in a given volume. In the second step, if a molecule of higher thermal energy migrates to a region of lower energy level, it must be distribute its excess energy among the long energy molecules. We assume the concentration of thermal energy to be constant in the given volume. The energy of molecules consists of kinetic energy and internal energy. The internal energy is associated with the random translation motion of molecules and internal motion of molecules. Energy balance. The principle of energy balance is similar to mass balance. The first law of thermodynamics, or the mechanical energy balance, is needed to provide the correct relationship of the many terms in the energy balance: molecular internal energy, potential energy, kinetic energy, radiant energy, electrical energy, magnetic energy, chemical reaction effects, heat supplied from external sources, and work done. Basic concepts upon which the technique of solving energy problems is based are the rate equations for the conservation of chemical spaces, conservation of mass, conservation of momentum, and conservation of energy.
Momentum has a direction as well as magnitude. Quantities that have both a magnitude and a direction are known as vector quantities. Because momentum has a direction, it can be used to predict the resulting direction of objects after they collide, as well as their speed. Below, the basic properties of momentum are described in one dimension. The vector equations are almost identical to the scalar equations. But if an object is at rest, it has no momentum. No matter how large is its mass, momentum is not the same as inertia. In contrast, a bullet can have a large momentum, even if it has a small mass, because it is moving at a high velocity. Also, there is momentum conservation in explosions. A firecracker placed in a stationary object will cause the object to explode. Before the explosion, the total system momentum is zero. Upon explosion, the object will break into a variety of fragments. The vector sum of the momentum of the individual fragments is zero. The total system momentum is the same before and after the explosion.
Convection is the movement of physical quantity, for example heat, because of the movement of the matter. For example, the wind is the movement of the earth, and it can cool down a room in the window. It is open because the cold air comes inside of the room. The movement of the clouds, the sea waves, and many types of heaters are examples of convections. Convection can happen naturally, natural convection, or because of moving device, forced convection. The fan is a device that produces the movement of air artificially. The air in this case is moving because of the rotation of the fan. This is an example of forced convection. Natural convection happens because a fluid is lighter if it's hot and it is heavier if it's cold, so its fluid has hot part and cold part. The hot part will naturally move and the cold part naturally moves downward.
Radiation is the emission or transmission of energy in the form of waves or particles through space or through a material medium.
The process of heat conduction depends on four basic factors: the temperature gradient, the cross-section of materials involved, their path length, and the properties of those materials. A temperature gradient is a physical quantity and describes in which direction and at what rate the temperature changes in a specific location. Temperature always flows from the hottest to coldest source due to the fact that cold is nothing but the absence of heat energy. This transfer between bodies continues until the temperature difference decays and a state known as thermal equilibrium occurs. Cross-section and path length are also important factors. The greater the size of the material involved in the transfer, the more heat is needed to warm it. Also, the more surface area that is exposed to open air, the greater likelihood for heat loss. So, shorter objects with a smaller cross-section are the best means of minimizing the loss of heat energy. Last but certainly not least is the physical properties of the materials involved. Basically, when it comes to conduction heat, not all substances are created equal. Metals and stone are considered good conductors since they can speedily transfer heat, whereas materials like wood, paper, air, and cloth have heat.
And now we are going to explain the heat conduction in a rectangular fin.
A simple rectangular fin is shown in this figure. The water temperature is Tw and the ambient temperature is Ta. Dimensions of fin are shown in this figure.
We have to formulate the problem and calculate the droplet temperature. Finally, also calculate the efficiency of the fin.
Before we start with the problem, let me explain you what is a fin. Fins are used in a large number of applications to increase the heat transfer from surfaces. Typically, the fin material has a high thermal conductivity. The fin is exposed to a flowing fluid which cools or heats it, with a high thermal conductivity allowing increased heat being conducted from the wall through the fin. The design of cooling fins is encountered in many situations, and we thus examine heat transfer in a fin as a way of defining some criteria for design. Fins are most commonly used in heat exchanging devices, such as radiators in cars, computer CPU heat sinks, and heat exchangers in power plants. They are also used in newer technology such as hydrogen fuel cells. Fins are so useful, and as we can see in all these pictures, fins are everywhere. So now that you know what is a fin, let's continue with the problem. Let's consider this figure.
Now, we must take that system is at steady state
fin has a constant heat conductivity, and the outside heat transfer coefficient is HA.
Consider a case when thickness of the fin is negligible in comparison with the height and width, where L and W is bigger than 2B. In this case, the heat flux in y direction is small, and we may write temperature as a function of x and z coordinates only. In this case, the equation of thermal energy may be simplified as this equation. This may also require numerical solutions. To find simple analytical solution, we may further assume that the average temperature T average at any across section of fin is a function of z coordinate only, as we see.
Thus, we are reducing the original two-dimensional into a one-dimensional problem to obtain an approximate solution. This assumption is reasonably valid since the thickness of the fin is very small, and the variation of temperature in x direction may be averaged out. Since we have reduced a two-dimensional problem to a one-dimensional problem by averaging the temperature, the equation of thermal energy is no longer applicable. We may use the shell energy balance approach to find an appropriate solution. For the sake of convenience, T is now replaced by T. The control volume is a strip of the fin with thickness 2b, length z, and width w as shown in this figure.
So now for the solution, we have to consider the heat entering in the control volume by conduction. We have this equation, so next we have the heat leaving the control volume by conduction. So it's almost the same equation. Now we have to consider the heat loss from upper and lower surfaces of the control volume, and we have this equation. Thus, energy balance may be written as this equation. And then if we divide this equation, we take the limit like delta z is to 0, we obtain this, and then we have to apply the Fourier's law.
Finally, we obtain this equation, that is the equation 2. The boundary conditions may be written as at z is 0 and t is tw, and at z is L, and we obtain the next equation. However, for a sufficiently long film is small, and we may assume that at z is L, and we are use this form. By applying the above boundary condition is equation 2, we obtain the following solution.
Well, considering these values, this equation may be arranged as we see in this equation, and then we have to solve with this one. So, going back to the original two-dimensional problem given in equation, even without assuming anything further, we may still obtain the same results as given by the last equation, provided B is very small. Thus, the fin temperature is the function of both x and z coordinates tensor, and the equation of the thermal energy may be written as this equation.
If 2b is small from the definition of a differential, we may approximate the first term as this equation by applying the boundary condition given in the equations, and we get the next equation, or this form, where the partial derivative is replaced by the total derivative. By substituting the above equation in the partial derivative, we again obtain this form.
For the last step, the partial derivative is replaced by the total derivative. After using the Fourier law of heat conduction, we obtain the following differential equation.
Efficiency of the rectangular fin. As stated above, the efficiency of fin may be defined as N is actual rate of heat loss from fin between rate of heat loss from an isothermal fin at Tw. Substituting the values, we get the next formula.
The last equation may be simplified by using the above dimensionless numbers defined in the equation and the other equation. So next, the above equation leads to the following simple solution,
which may be further simplified as this form.
As may be noted from above equation, n only depends on n. A simple plot for n versus n is shown below. This figure shows that long fins have lesser efficiency. The optimum fin length may be found by optimizing the enhancement in heat transfer and the cost of this additional surface area. In the real life, the fins need not to be rectangular in shape, and the different shaped fins may be designed for enhanced fin efficiency. And that's all. We have finished this problem using heat transfer.
Thanks for watching. See you next video. Bye.
Why does stirring help to mix milk in your coffee? How long does a hot product need to be cooled down before further handling can take place? How fast does a bubble in a glass of champagne rise? And why does it grow? How fast does a hailstone come down? Transport phenomena is basic to many engineering fields. It covers the how and why three important quantities, mass, energy and momentum, are transported in applications. It can be done in a unified way, showing the strong similarities between transport of mass, energy and momentum. Hi, I'm Robert Mudde and I'm a teacher in this course. I started working in Delft University in 1988 and I found a keen interest in multiphase flows and transport phenomena. Delft University is one of the starting points of transport phenomena. It took until 1956 before fluid mechanics, heat and mass transfer were approached in a unified way. It was Bird and Kramers who, in this very building, discussed their ideas, the building we still use today. The ideas and laws of transport phenomena are applied in chemical engineering, biotechnology, civil engineering, mechanical engineering, applied physics and aeronautics. In this course we will introduce the basic concepts such as the balance equation, that is a universal tool helping getting a grip on the examples given earlier. And you will discover that transport phenomena are everywhere, from small everyday life scenarios to big industrial processes, from inside the human body to large-scale weather phenomena. In this course we target a wide range of students as well as professionals who need to apply the principles of transport phenomena and experience a lack in their basic understanding. At the end of the course, you will be able to quantitatively solve a whole variety of engineering problems. And you will be prepared to take on advanced courses in the area of transport phenomena and fluid mechanics. A background in basic calculus, including elementary differential equations, some mechanics and a bit of thermodynamics is required. After this course your life will not be the same anymore. You will see the world through different eyes. You will see the connections, and it will change your view on cooking, walking in the rain, industrial processes, sustainable solutions, energy efficiency and many more. Are you ready to take on the challenge? Join us and master transport phenomena.